In the frozen darkness of space, something unimaginable lurks. A star 20 times heavier than our sun has collapsed into a sphere smaller than Manhattan. Yet it possesses a magnetic field 1 quadrillion times stronger than anything on Earth. This cosmic monster can tear apart atoms from thousands of miles away and unleash more energy in 1 second than our sun produces in centuries. Tonight, we journey to Magnetars, planets made of pure metal rain and explosions so violent they rewrite the laws of physics. If you enjoy discovering the universe's most terrifying secrets, hit that like button. Prepare yourselves, we begin. Picture a star so massive that our sun looks like a grain of sand beside a basketball. This cosmic giant burns through its nuclear fuel at an incredible rate, living fast and dying young in just 10 million years. While our sun will shine steadily for 10 billion years, these stellar behemoths race toward their doom. When the fuel runs out, gravity wins the ultimate battle. The star's core collapses in less than 1 second. Imagine cramming the entire mass of our sun into a sphere just 12 miles across. The collapse happens so fast that if you could watch it from space, you would see the star's surface falling inward at 30,000 miles per second. The core becomes so dense that a teaspoon of this material would weigh 6 billion tons on Earth. That is heavier than Mount Everest, compressed into something smaller than a sugar cube. The temperature soars to 100 billion degrees, hot enough to fuse iron atoms together. Meanwhile, the star's outer layers keep falling inward, completely unaware that the core has already collapsed. When these layers finally crash into the ultra-dense core, they bounce back like a rubber ball hitting concrete. This creates a shock wave that rips through the star at 20,000 miles per second. The explosion that follows makes our most powerful nuclear weapons look like firecrackers. In just 10 seconds, this dying star releases more energy than our sun will produce in its entire 10 billion year lifetime. The blast is so bright it can outshine an entire galaxy containing 400 billion stars. But here is where things get truly strange. While most of these stellar explosions create ordinary neutron stars, roughly 1 in 10 create something far more exotic and dangerous. The magnetic fields generated during this cosmic catastrophe become twisted and amplified beyond anything found elsewhere in the universe. These rare monsters spin as fast as a kitchen blender, completing 1 full rotation every few seconds. Their surfaces reach temperatures of 18 million degrees, hot enough to vaporize any known material instantly. They shoot beams of deadly radiation across thousands of light years of space, like cosmic lighthouses gone mad. The magnetic forces surrounding these objects are so powerful they could erase every credit card on Earth from the distance of the moon. They warp space-time itself, creating gravitational effects that challenge our understanding of physics. What emerges from this stellar death is not just any neutron star, but something far more terrifying and mysterious. These cosmic monsters have magnetic fields 1 quadrillion times stronger than Earth, and they hide secrets that could change everything we know about the universe. But first, we must understand exactly what makes these objects so impossibly dense. Stand in the middle of Manhattan and look around at the towering skyscrapers, the millions of people, and the countless tons of concrete and steel. Now imagine crushing all of that down to the size of a pinhead while somehow keeping every single atom intact. That gives you just the beginning of understanding neutron star density. A magnetar measures only 12 miles across, roughly the distance from Manhattan to the Bronx. Yet packed inside this tiny sphere is more matter than exists in our sun. All 8 planets, every moon, asteroid, and grain of cosmic dust in our entire solar system combined. The numbers are so extreme they break our everyday understanding of matter itself. To achieve this impossible density, the magnetar's gravity performs the ultimate magic trick. It squeezes matter so hard that the empty space inside atoms simply disappears. Think of atoms like mostly empty concert halls with tiny dancers performing in the center. Under normal conditions, these dancers have plenty of room to move around, but inside a magnetar, the concert hall walls collapse completely. The crushing force pushes protons and electrons together so violently that they merge into neutrons, creating a new form of matter that cannot exist anywhere else in the universe. The entire star becomes one giant atomic nucleus, the largest single object made of pure nuclear matter. A sugar cube of magnetar material would weigh 1 billion tons, roughly equivalent to every car, truck, and bus currently driving on Earth's roads. Drop this sugar cube from waist height and it would punch through the Earth's crust, mantle, and core like a bullet through tissue paper, creating a tunnel straight through to the other side of our planet. The magnetar's surface gravity is 200 billion times stronger than Earth's. If you weigh 150 pounds on Earth, you would weigh 30 trillion pounds on a magnetar surface. Your body would be flattened to a thickness thinner than a human hair in less than a microsecond. Walking across a magnetar surface would require overcoming gravitational forces stronger than the thrust of a Saturn V rocket. Each step would feel like trying to lift a mountain. The escape velocity reaches 100,000 miles per second, which is 1/3 the speed of light itself. Even light struggles to escape this gravitational prison. Photons climbing out of the magnetar's gravity lose energy and become redshifted, appearing dimmer and redder than when they started their journey. Time itself slows down compared to the rest of the universe due to extreme gravitational time dilation effects. Yet density is only the beginning of the magnetar's impossible properties. The magnetic fields surrounding these objects create forces that make their incredible gravity seem gentle by comparison. These magnetic monsters generate fields so powerful they reshape the very structure of empty space. Earth's magnetic field gently guides compass needles and creates beautiful auroras when solar particles dance across our atmosphere. The strongest magnets in hospital MRI machines generate fields about 10,000 times more powerful than Earth's natural magnetism. But magnetars laugh at these puny forces like hurricanes scoff at gentle breezes. A magnetar's magnetic field reaches 1 quadrillion times the strength of Earth's magnetic field. To understand this mind-bending number, imagine taking every magnet on Earth, from refrigerator decorations to industrial electromagnets, and multiplying their combined strength by 1 billion billion. That still falls short of a magnetar's magnetic fury. These impossible fields form during the star's violent death throes when the stellar core collapses in less than 1 second. Picture a figure skater pulling in her arms during a spin. As she gets smaller, she spins faster due to conservation of angular momentum. The same thing happens during stellar collapse, but instead of a graceful pirouette, you get cosmic chaos. The collapsing stellar core spins faster and faster, reaching rotation speeds of over 1,000 times per second. At the same time, the star's original magnetic field gets compressed and twisted like taffy in a cosmic blender. The combination of rapid rotation and compression amplifies the magnetic field by factors that boggle the mind. The magnetic field lines become so tightly wound that they store tremendous amounts of energy, like rubber bands stretched to their breaking point. These field lines thread through the magnetar's crust and extend thousands of miles into space, creating invisible highways for charged particles to travel at nearly the speed of light. Near the magnetar's surface, the magnetic field becomes so strong it fundamentally changes how atoms behave. Hydrogen atoms, normally round like tiny spheres, get stretched into needle-thin cigars aligned with the magnetic field lines. The familiar electron orbitals taught in chemistry class completely reshape themselves under these extreme conditions. The magnetic forces near a magnetar are powerful enough to levitate diamagnetic materials like water, carbon, and even human tissue. If you somehow survived the deadly radiation and crushing gravity, the magnetic field would literally lift your body off the surface and align every atom in your bones and blood with the field lines. At distances of just 600 miles from the magnetar, the magnetic field becomes strong enough to make X-ray photons split apart or merge together, processes that are impossible under normal physics. The field warps the quantum vacuum itself, creating virtual particles that pop into existence and disappear in fractions of a second. These magnetic monsters even affect the structure of empty space around them, making the vacuum behave like a thick, viscous fluid rather than nothingness. Light waves traveling through this magnetized vacuum can actually change their polarization and energy levels, but the most terrifying aspect of magnetar magnetic fields is their instability. like overstretched rubber bands, these cosmic magnetic highways can suddenly snap without warning, unleashing catastrophic energy bursts that can be detected from across the galaxy. Imagine standing 1,000 miles away from a magnetar, roughly the distance from New York to Atlanta. You might think this safe distance would protect you from the cosmic monster's influence. You would be tragically wrong. The magnetar's magnetic field at this distance still exceeds the strongest magnets ever created on Earth by factors of millions. At 1,000 miles away, the magnetar's magnetic field would begin rearranging the very atoms inside your body. The electrons orbiting atomic nuclei would shift into new configurations never seen in Earth's gentle magnetic environment. Your body chemistry would start changing at the molecular level as magnetic forces override the electromagnetic bonds holding your cells together. Move closer to 500 miles, and the magnetic field reaches strengths that make the atomic bonds in your DNA completely unstable. The delicate double helix structure that carries your genetic code would begin unwinding as magnetic forces pull on the electrons that create chemical bonds between base pairs. Your chromosomes would literally dissolve at the molecular level. At 100 miles away, roughly the distance from Washington, D.C. to Philadelphia, the magnetic field becomes so intense it overcomes the electromagnetic force holding electrons in their atomic orbitals. Picture electrons like planets orbiting the sun, but now imagine a gravitational field so strong it rips the planets from their orbits and sends them flying into space. Your body contains roughly 7 octillion atoms, each one held together by electromagnetic forces. The magnetar's field would systematically destroy these bonds, starting with the outermost electrons and working inward toward atomic nuclei. You would not just die. Your physical matter would cease to exist in any recognizable form. At 50 miles away, the magnetic field reaches the critical threshold where even atomic nuclei begin breaking apart. Protons and neutrons, bound together by the strongest force in nature called the strong nuclear force, would be ripped away from each other like puzzle pieces scattered by a tornado. The process happens faster than nerve signals can travel through your brain. Before your neurons could register pain or fear, every atom in your body would be reduced to a cloud of individual subatomic particles streaming away in all directions along magnetic field lines. But the magnetar's deadly influence extends far beyond direct atomic destruction. At distances of several thousand miles, the magnetic field creates powerful electric currents in any conducting material. The iron in your blood would heat up like metal in a microwave oven, cooking you from the inside out. The magnetar also generates intense beams of gamma rays that travel at the speed of light. These high-energy photons carry enough power to shatter atomic nuclei and create radioactive isotopes throughout your body tissue. Even if you somehow survived the magnetic effects, the radiation dose would be millions of times greater than the amount that causes immediate death. Spacecraft electronics would fail instantly at distances of thousands of miles, as magnetic fields induce electrical currents that overload circuits designed for Earth's gentle magnetic environment. Navigation systems would spin wildly as compass readings become meaningless in the presence of magnetic forces beyond human comprehension. The magnetar's influence creates a sphere of absolute destruction extending thousands of miles in all directions, a cosmic no-fly zone where matter itself cannot maintain its familiar structure. For decades, astronomers searched the cosmos with increasingly powerful telescopes, mapping stars, galaxies, and nebulae across billions of light years. They discovered pulsars spinning like cosmic lighthouses and black holes devouring nearby matter. But magnetars remained completely hidden, invisible ghosts lurking in the darkness between stars. The breakthrough came not from patient observation, but from pure cosmic luck. On March 5, 1979, a network of satellites designed to detect nuclear weapons tests suddenly registered an intense burst of gamma rays flooding Earth's atmosphere. The energy signature looked unlike any nuclear explosion ever recorded. Scientists initially suspected the signal came from enemy nations testing secret weapons in space. Military officials scrambled to determine if the United States was under attack by some new form of electromagnetic warfare. The gamma ray burst was so powerful it temporarily blinded satellite sensors and caused radio blackouts across the planet. Within hours, astronomers realized something extraordinary had occurred. The gamma rays had not originated from Earth or even our solar system. The burst came from the direction of the Large Magellanic Cloud, a small galaxy orbiting our Milky Way at a distance of 160,000 light-years. The energy release was beyond anything scientists had ever recorded. In just 1/10 of a second, this mysterious object had released more energy than our sun produces in 1,000 years. The burst was so bright that it bounced off the moon's surface and created detectable reflections in Earth's upper atmosphere. More satellite networks around the world confirmed the incredible numbers. The gamma-ray burst had temporarily become the brightest object in the known universe, outshining entire galaxies containing hundreds of billions of stars. Yet, when astronomers pointed their most powerful optical telescopes toward the source location, they saw absolutely nothing. The invisible object had somehow generated this cosmic explosion and then vanished back into darkness like a phantom. For years, scientists debated what could possibly create such enormous energy releases while remaining completely invisible to traditional telescopes. The mystery deepened when similar bursts began appearing from other locations across our galaxy. Each event lasted only seconds or minutes, but released energy equivalent to major stellar explosions. The sources appeared randomly in the sky with no predictable pattern, making them nearly impossible to study. Breakthrough technology finally revealed the truth in the 1990s, when X-ray telescopes sensitive enough to detect extremely hot objects were launched into space. These instruments could peer through cosmic dust clouds and detect the faint X-ray glow from objects too dim for optical telescopes to see. The X-ray observations revealed that the mysterious burst sources were actually neutron stars, but neutron stars unlike any previously discovered. These objects spun more slowly than typical pulsars and possessed magnetic fields thousands of times more powerful than anything astronomers had ever measured. The name magnetar was coined to describe these magnetic monsters, combining the words magnetic and star into a term that captures their fundamental nature as cosmic objects dominated by magnetic forces rather than gravity or nuclear fusion. Scientists realized they had discovered an entirely new class of stellar objects, invisible titans hiding throughout our galaxy and capable of explosive outbursts that can be detected from millions of light years away. Our Milky Way galaxy contains over 400 billion stars, ranging from tiny red dwarfs barely larger than Jupiter to blue supergiants hundreds of times more massive than our sun. Among all these stellar multitudes, astronomers have confirmed the existence of only about 30 magnetars, making them rarer than winning lottery tickets in a cosmic game of chance. The rarity begins with the specific conditions required for magnetar formation. Only stars between 10 and 25 times the mass of our sun can potentially become magnetars when they die. Stars lighter than this threshold become white dwarfs or ordinary neutron stars, while stars heavier than 25 solar masses collapse directly into black holes, skipping the magnetar phase entirely. Even having the right mass provides no guarantee of magnetar formation. The dying star must possess an unusually strong magnetic field before its collapse begins. Most massive stars have relatively weak magnetic fields, similar to our sun's gentle magnetism amplified by size. Only about 1% of massive stars develop the powerful magnetic fields necessary for magnetar creation. The stellar rotation rate during collapse also plays a crucial role. The star must spin at just the right speed to amplify its magnetic field during the collapse process. Too slow, and the magnetic field fails to reach magnetar strength. Too fast, and the rapid rotation tears the forming neutron star apart before it can stabilize. The collapse itself must proceed under very specific conditions. The shockwave from the stellar explosion needs to be perfectly timed and positioned to compress and twist the magnetic field lines into their final, incredibly powerful configuration. This delicate balance occurs in less than 1% of massive star deaths. Even if all these conditions align perfectly, the resulting magnetar faces additional survival challenges. The intense magnetic fields make these objects extremely unstable compared to ordinary neutron stars. Many newly formed magnetars likely destroy themselves within a few thousand years through magnetic field decay and explosive outbursts. The observable lifetime of active magnetars spans only about 10,000 years, a cosmic blink of an eye compared to the billions of years that ordinary neutron stars remain detectable. After this brief period, magnetars lose their intense magnetic fields and fade into darkness, becoming virtually impossible to distinguish from the millions of dead neutron stars scattered throughout our galaxy. This short, active lifetime means that astronomers can only detect magnetars during a tiny fraction of their existence. For every magnetar we currently observe, thousands of others have already burned out and become invisible. The 30 known magnetars represent just the tip of a much larger iceberg of extinct magnetic monsters. Geographic distribution also limits magnetar discovery. These objects cluster primarily in the dense star-forming regions near our galaxy's center, where massive stars are more common. The outer regions of the Milky Way, where Earth resides, contain fewer massive stars and therefore fewer potential magnetar birthplaces. Detection technology provides another limiting factor. Magnetars emit most of their energy as X-rays and gamma rays, requiring specialized space telescopes to observe them. Ground-based optical telescopes cannot detect these invisible objects, and many magnetars remain undiscovered because their X-ray emissions are too faint for current instruments to detect from Earth's distance. The combination of these factors creates a perfect storm of rarity, making magnetars among the most exclusive objects in our cosmic neighborhood. Earth's most devastating earthquakes release energy equivalent to thousands of nuclear bombs, toppling skyscrapers and reshaping coastlines. The strongest earthquake ever recorded reached magnitude 9.5, powerful enough to be felt around the entire planet. But magnetar quakes make our worst natural disasters look like gentle tremors by comparison. A typical magnetar quake releases more energy in 1 second than all of Earth's earthquakes combined over the past 1 million years. The smallest detectable magnetar starquake carries the explosive power of 1 trillion nuclear bombs detonating simultaneously. These are not just earthquakes, they are cosmic catastrophes that rearrange matter at the nuclear level. The quakes begin deep inside the magnetar's ultra-dense crust, where matter exists in forms impossible anywhere else in the universe. Picture atomic nuclei arranged in crystalline structures harder than diamond, yet subject to magnetic stresses that would vaporize any normal material instantly. This crust bears magnetic pressures equivalent to the weight of Mount Everest, pressing down on every square inch. As the magnetar's magnetic field slowly evolves and shifts, it creates increasing stress within the crystalline crust. The crust acts like a rigid shell trying to contain magnetic forces that want to rearrange themselves into more stable configurations. Imagine a steel container holding an explosion that grows stronger every second. When the stress finally exceeds the crust's incredible strength, fractures propagate at nearly the speed of light. Entire mountain ranges of ultra-dense matter shift position in microseconds. The breaking crystal lattices release stored magnetic energy like snapping rubber bands. But with forces measured in the power output of entire stars, the quake sends seismic waves racing around the magnetar surface at thousands of miles per second. These waves carry so much energy they heat the neutron star's surface to temperatures exceeding 50 million degrees, hot enough to trigger nuclear fusion reactions in the thin atmosphere above the crust. The magnetic field lines threading through the fractured crust suddenly snap and reconnect in explosive magnetic reconnection events. This process converts magnetic energy directly into kinetic energy, accelerating charged particles to nearly the speed of light and creating intense bursts of X-rays and gamma rays. The starquake also causes the magnetar's rotation to change suddenly, like a figure skater extending her arms during a spin. This change in rotation speed can be detected by astronomers on Earth as a glitch in the magnetar's regular pulsing pattern. The rotation changes are so abrupt, they would be equivalent to Earth's day suddenly becoming several seconds shorter. The energy released during major magnetar quakes propagates through space as gravitational waves, ripples in spacetime itself that travel at light speed. While these waves are too weak to detect with current technology, they represent distortions in the fabric of reality caused by matter moving under the influence of magnetic fields stronger than anything else in the known universe. The most powerful magnetar quake ever observed, recorded from SGR 1806-20, released enough energy to power human civilization for over 1 million years. The burst was so intense it temporarily overwhelmed X-ray detectors on satellites throughout the solar system and caused measurable changes in Earth's upper atmosphere from a distance of 50,000 light-years. These cosmic earthquakes reveal that magnetars are not stable, dead objects, but dynamic systems where magnetic forces constantly battle against the strongest materials in existence. The surface of our sun burns at a scorching 10,000 degrees Fahrenheit, hot enough to vaporize any known material and bright enough to blind anyone who looks directly at it. Yet, a magnetar's surface reaches temperatures of 18 million degrees Fahrenheit, nearly 2,000 times hotter than our local star. This creates one of the most extreme temperature gradients in the known universe. At 18 million degrees, the magnetar's surface exists in a state of matter called a plasma, where atoms are completely stripped of their electrons and exist as bare nuclei swimming in a sea of free electrons. The surface glows with intense X-ray radiation that would instantly kill any living thing within thousands of light years if focused in their direction. The extreme surface heat comes from magnetic friction, as the magnetar's incredibly powerful magnetic field lines constantly shift and reconnect above the neutron star's crust. Picture millions of invisible rubber bands stretching, snapping, and reforming every second. With each reconnection event releasing energy equivalent to hydrogen bomb explosions, charged particles accelerated by the magnetic fields crash into the magnetar surface at nearly the speed of light, depositing enormous amounts of kinetic energy that converts directly to heat. The bombardment is so intense that the surface material undergoes continuous nuclear reactions, fusing lighter elements into heavier ones and releasing additional thermal energy. Yet, just a few miles below this hellish surface lies one of the coldest environments in the universe. The magnetar's core temperature measures only about 1 million degrees, roughly 1/18 the temperature of the burning surface above. This seems to violate everything we know about heat flow and thermodynamics. The mystery lies in the magnetar's unique thermal properties. Normal materials conduct heat from hot regions to cold regions through atomic vibrations and electron movement. But inside a magnetar, the intense magnetic field creates barriers that prevent normal heat conduction from occurring. The magnetic field lines act like invisible walls that block heat from flowing inward toward the core. Electrons, which normally carry thermal energy through materials, become trapped along magnetic field lines and cannot move freely in other directions. This creates thermal insulation more effective than any material found on Earth. The magnetar's crystalline crust also contributes to the temperature isolation. The ultra-dense nuclear matter forms perfect crystals with very few defects or impurities. These perfect crystals conduct heat much more slowly than normal materials, creating additional insulation between the hot surface and cold core. Neutrinos provide the primary cooling mechanism for the magnetar's interior. These nearly massless particles can pass through the intense magnetic fields without being affected and carry thermal energy away from the core at nearly the speed of light. The neutrino cooling rate is so efficient that it keeps the interior temperature much lower than the surface. The temperature difference creates convection currents within the magnetar's outer layers, where hotter material rises toward the surface, while cooler material sinks deeper. But the magnetic field disrupts these convection patterns, creating complex circulation cells that further complicate heat transfer. This extreme temperature gradient means that a magnetar simultaneously exists as one of the hottest and coldest objects in the universe, with surface conditions hot enough to trigger nuclear fusion and interior conditions cold enough to allow matter to exist in exotic quantum states impossible at higher temperatures. Picture Earth spinning so fast that a single day lasts only 10 seconds instead of 24 hours. Cities would fly apart from centrifugal force, oceans would become airborne, and the planet itself would stretch into an egg shape before finally disintegrating. Yet, young magnetars routinely spin at rates that would tear normal matter apart in microseconds. The fastest spinning magnetar ever discovered designated PSR J748-2446, completes one full rotation every 1.3 seconds. This means its equatorial surface travels at roughly 15,000 miles per second, which is 5% the speed of light. At these rotation rates, the magnetar shape becomes noticeably flattened, bulging outward at its equator like a cosmic spinning top. The centrifugal forces generated by this incredible spin rate would instantly destroy any normal material. Picture trying to hold on to a merry-go-round spinning at 15,000 miles per second. Even the strongest steel would snap like wet tissue paper under such extreme rotational stress. Only matter compressed to nuclear density possesses sufficient structural strength to maintain cohesion at these spinning speeds. As the magnetar rotates, its powerful magnetic field lines sweep through space like the rotating beam of a lighthouse. But instead of visible light, these cosmic lighthouses emit deadly beams of X-rays and gamma rays that slice through the vacuum at nearly the speed of light. Any matter caught in these rotating beams experiences intense electromagnetic acceleration. The spinning magnetic field creates enormous electrical voltages across the magnetar surface, generating potential differences of 1 quadrillion volts between the magnetic poles and equator. For comparison, the highest voltage power lines on Earth carry only about 800,000 volts. Lightning bolts, nature's most spectacular electrical displays, involve voltages of roughly 100 million volts. These tremendous voltages accelerate charged particles to incredible speeds. Electrons and protons caught in the magnetar's magnetic field lines get boosted to energies millions of times higher than particles in Earth's most powerful accelerators. The magnetar essentially becomes a natural particle accelerator the size of a city. The rapid rotation also generates powerful gravitational waves as the magnetar's slightly non-spherical shape creates ripples in spacetime itself. These waves carry energy away from the magnetar, causing its rotation to gradually slow down over thousands of years. Each rotation removes a tiny amount of rotational energy that propagates outward at the speed of light. Fast-spinning magnetars experience additional complications from their magnetic field geometry. The rapid rotation causes magnetic field lines to become twisted and tangled like cosmic spaghetti. When these twisted field lines suddenly snap and reconnect, they release tremendous bursts of energy that can briefly outshine entire galaxies. The magnetar's rapid spin creates a wind of charged particles streaming away from its surface at speeds approaching the speed of light. This magnetar wind carries magnetic field lines far into space, creating a magnetosphere that extends thousands of miles from the neutron star's surface. Any material entering this magnetosphere gets caught up in the magnetic field and accelerated to relativistic speeds. The combination of rapid rotation and intense magnetic fields makes young magnetars among the most dynamic and energetic objects in the universe. Cosmic engines that convert rotational energy into electromagnetic radiation with incredible efficiency. But this furious spinning cannot last forever, and the consequences of a magnetar's gradual slowdown create entirely new forms of cosmic violence. Every magnetar begins its existence spinning at incredible speeds. But like cosmic tops gradually losing momentum, they all face an inevitable slowdown that transforms them into even more dangerous objects. The process occurs over thousands of years and creates some of the most violent events in the known universe. Young magnetars lose rotational energy through multiple mechanisms working simultaneously. The primary culprit is electromagnetic braking, where the spinning magnetic field acts like a cosmic generator, producing electrical currents that flow through the surrounding space plasma. These currents create resistance that opposes the magnetar's rotation, similar to how applying brakes slows down a spinning wheel. The magnetar's powerful magnetic field extends thousands of miles into space, dragging ionized particles along with the rotation. As these particles accelerate to high speeds, they radiate electromagnetic energy that carries momentum away from the system. The magnetar essentially powers a cosmic light show that gradually robs it of rotational energy. Gravitational wave emission provides another energy drain. The magnetar's slightly non-spherical shape creates ripples in spacetime that propagate outward at the speed of light, carrying rotational energy with them. While individually tiny, these gravitational waves continuously remove energy from the spinning neutron star over millions of years. As the magnetar slows down, its magnetic field structure becomes increasingly unstable. The field lines, originally organized by rapid rotation, begin to tangle and twist like cosmic spaghetti left to its own devices. These twisted magnetic structures store tremendous amounts of energy, like overstressed rubber bands ready to snap. When magnetic field lines finally become too twisted to remain stable, they undergo explosive reconnection events. Imagine millions of stretched rubber bands snapping simultaneously while releasing energy equivalent to nuclear explosions. The magnetic reconnection heats the magnetar surface and accelerates particles to nearly the speed of light. The slowing rotation also affects the magnetar's internal structure. The neutron star's crust, which formed under the stress of rapid rotation, cannot quickly adjust to changing rotational speeds. This creates internal stress that builds up over years until the crust finally fractures in violent starquakes that can be detected from thousands of light years away. Older magnetars that have slowed significantly develop a different behavior pattern known as bursting activity, instead of the steady energy output of rapidly spinning magnetars. Older objects produce sporadic but incredibly powerful outbursts. These bursts can release more energy in a few seconds than our sun produces in months. The bursting behavior occurs because slow rotation allows magnetic field lines to become more severely twisted before snapping. When reconnection finally occurs, the energy release is more concentrated and violent than the smaller, more frequent events seen in rapidly spinning magnetars. It is like the difference between many small firecrackers and one massive explosion. Some magnetars enter dormant phases where they become almost completely inactive for years or decades, only to suddenly reawaken with burst activity that can briefly make them among the brightest X-ray sources in our galaxy. This unpredictable behavior makes magnetars particularly challenging to study and monitor. The slowdown process also changes how magnetars interact with their environment. Rapidly spinning magnetars create powerful particle winds that clear away nearby material, while slower magnetars may accumulate matter from surrounding space. This accumulated material can fall onto the magnetar surface and trigger additional X-ray emissions through gravitational heating. Eventually, all magnetars slow down enough that their magnetic fields begin to decay significantly, transforming these cosmic monsters into quiet, nearly invisible neutron stars that may persist for billions of years in their post-magnetar state. The space around a magnetar transforms into a cosmic hurricane zone where ordinary physics breaks down and matter exists in states impossible anywhere else in the universe. These invisible storms extend millions of miles from the neutron star's surface, creating electromagnetic tempests that dwarf any weather phenomenon Earth has ever experienced. The storms begin at the magnetar surface, where magnetic field lines emerge from the neutron star, like cosmic highways for charged particles. The intense magnetic fields accelerate electrons and protons to speeds approaching 99% the speed of light, stripping them completely away from the magnetar's gravitational grip and hurling them into surrounding space. These relativistic particles carry enormous amounts of kinetic energy as they stream outward along magnetic field lines. When particles moving at different speeds collide, they create shock waves that heat the surrounding plasma to temperatures exceeding 100 million degrees. The result is a magnetosphere filled with superheated gas that glows intensely in X-ray wavelengths. The magnetar's rotation adds complexity to these plasma storms by twisting magnetic field lines into helical shapes like cosmic corkscrews. As the neutron star spins, it drags magnetic field lines through the surrounding plasma, creating electrical currents that flow for millions of miles through seemingly empty space. These currents generate their own magnetic fields that interact with the original magnetar field in chaotic, unpredictable ways. When magnetic field lines under extreme stress finally snap and reconnect, they release stored magnetic energy in explosive events called magnetic reconnection. Picture two cosmic rubber bands stretched to their breaking point, suddenly snapping and reforming in new configurations. The energy release accelerates particles to even higher speeds and creates intense bursts of electromagnetic radiation. The plasma storms exhibit complex wave behavior as different regions oscillate at various frequencies. Alfvén waves, named after physicist Hannes Alfvén, propagate through the magnetized plasma like ripples on a pond, but at speeds of thousands of miles per second. These waves can travel millions of miles from the magnetar while carrying energy and momentum throughout the surrounding space. Magnetic bubbles form when regions of twisted field lines become isolated from the main magnetic structure. These bubbles, each one larger than Earth's orbit around the Sun, drift through the magnetosphere like cosmic soap bubbles filled with superheated plasma and high-energy particles. When bubbles collide or merge, they create additional energy releases and particle acceleration. The storms also generate powerful radio emissions as relativistic electrons spiral around magnetic field lines, producing synchrotron radiation that can be detected by radio telescopes on Earth. The radio signals provide astronomers with a way to study the invisible plasma environment surrounding magnetars from thousands of light years away. Turbulence within the plasma creates cascading energy transfer from large-scale magnetic structures down to smaller and smaller scales. Similar to how water flowing over rocks creates eddies and whirlpools, this turbulent cascade efficiently converts magnetic energy into particle kinetic energy and electromagnetic radiation. The plasma storms surrounding magnetars create natural laboratories for studying extreme physics impossible to replicate on Earth. The magnetic field strengths, particle energies, and plasma densities far exceed anything achievable with current technology, providing insights into fundamental physical processes that operate throughout the universe. These cosmic storms also influence the magnetar's immediate environment, clearing away interstellar material and creating cavities in surrounding gas clouds that can persist long after the magnetar itself has moved to a different location. Every few days, satellites orbiting Earth detect flashes of gamma rays so intense they briefly outshine the entire observable universe. These gamma ray bursts represent the most powerful explosions known to science, releasing more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. For decades, astronomers puzzled over what could create such incredible displays of cosmic violence. The mystery deepened when scientists realized that gamma ray bursts appeared randomly across the sky with no obvious pattern or preferred location. Some lasted only milliseconds, while others continued for several minutes. The energy requirements seemed to defy known physics, leading to increasingly exotic explanations involving alien civilizations, colliding black holes, or entirely new forms of matter. The breakthrough came when astronomers discovered that certain types of gamma-ray bursts originate from within our own Milky Way galaxy, specifically from regions where magnetars are known to exist. On December 27, 2004, a magnetar called SGR 1806-20 unleashed a gamma-ray burst so powerful it temporarily blinded satellites throughout the solar system and affected Earth's upper atmosphere from a distance of 50,000 light-years. This single event released more energy than our sun produces in 150,000 years, all compressed into 1/10 of a second. The burst was so bright that it bounced off the moon's surface and created detectable reflections in Earth's ionosphere. Radio telescopes detected the event's afterglow for months afterward. As shockwaves propagated through interstellar space, scientists realized they had witnessed a magnetar hyperflare. An explosion triggered when magnetic field lines under extreme stress suddenly snapped and reconnected on a massive scale. The process converts magnetic energy directly into gamma rays with incredible efficiency, creating brief but incredibly intense bursts of the most energetic form of electromagnetic radiation. The connection between magnetars and gamma ray bursts extends beyond our galaxy. Astronomers now believe that highly magnetized neutron stars in distant galaxies produce similar hyperflares that appear as short gamma-ray bursts when viewed from Earth. The extreme distances involved make these events appear much brighter than they actually are, creating the illusion of universe-spanning explosions. Some gamma-ray bursts may occur when magnetars undergo catastrophic magnetic field reconfigurations that completely restructure their magnetospheres. These global magnetic reorganization events release stored magnetic energy equivalent to the gravitational binding energy of entire planets, creating explosions visible across billions of light years of space. The most extreme gamma-ray bursts might result from magnetar collisions, where two highly magnetized neutron stars spiral into each other and merge in a cosmic catastrophe that briefly creates the strongest magnetic fields possible in the universe. The collision would trigger magnetic reconnection on a scale never seen from single magnetar events. Recent observations suggest that gamma-ray bursts from magnetars exhibit different characteristics than those produced by other mechanisms. Magnetar bursts tend to have shorter durations and display specific patterns in their gamma-ray spectra that serve as cosmic fingerprints identifying their magnetar origins. The study of magnetar-generated gamma-ray bursts provides astronomers with a way to detect and study these magnetic monsters in distant galaxies where individual magnetars are too faint to observe directly. Each burst acts like a cosmic beacon, announcing the presence of extreme magnetic fields in regions of space millions of light years away. Understanding this connection has revolutionized gamma-ray burst astronomy and revealed that magnetars play a much more important role in cosmic evolution than previously suspected. These magnetic monsters serve as cosmic laboratories where the universe tests the limits of physics under the most extreme conditions imaginable. Our sun converts 4 million tons of matter into pure energy every single second through nuclear fusion, following Einstein's famous equation E=mc². This incredible rate of energy production has powered our solar system for 4 billion years and will continue for another 5 billion years. Yet a single magnetar outburst lasting just 1/10 of a second can exceed our sun's century-spanning energy output. The secret lies in the magnetar's ability to store vast amounts of energy in its twisted magnetic field lines, like cosmic springs wound up to their breaking point. The magnetic field contains roughly the same amount of stored energy as the entire gravitational binding energy that holds the neutron star together. This represents energy equivalent to the complete annihilation of several Earth masses converted directly into pure electromagnetic radiation. When magnetic field lines under extreme stress finally snap and reconnect, they release this stored energy almost instantaneously. The process occurs much faster than nuclear fusion, which requires multiple steps and intermediate particles to convert mass into energy. Magnetic reconnection converts field energy directly into kinetic energy of charged particles and electromagnetic radiation with nearly 100% efficiency. The magnetar surface area plays a crucial role in amplifying the energy release. While our sun gradually releases energy from its vast surface over billions of years, a magnetar concentrates enormous energy release into a surface area only 12 miles across. This creates energy densities millions of times higher than anything our sun can produce, resulting in surface temperatures that briefly exceed 1 billion degrees. The reconnection process creates a cascade effect where initial magnetic snapping triggers additional reconnection events throughout the magnetosphere. Like dominoes falling in sequence, each reconnection event destabilizes neighboring magnetic structures, creating a chain reaction that can involve the magnetar's entire magnetic field system simultaneously. Particle acceleration during magnetar outbursts reaches energy levels that make the sun's particle emissions look gentle by comparison. Electrons and protons get boosted to speeds exceeding 99.9% the speed of light, carrying individual particle energies billions of times higher than anything achieved in Earth's most powerful particle accelerators. The magnetar's incredible density contributes to the energy release by providing enormous amounts of matter in a very small volume. When magnetic forces accelerate this ultra-dense material, even tiny amounts of moving matter carry tremendous kinetic energy due to the extreme mass density. A teaspoon of magnetar material moving at relativistic speeds carries more energy than all the moving vehicles on Earth combined. Gravitational energy conversion also amplifies magnetar outbursts. The intense gravity near the neutron star's surface converts potential energy into kinetic energy as accelerated particles fall back toward the magnetar. This gravitational energy gain can double or triple the total energy release compared to magnetic reconnection alone. The burst geometry focuses energy release into narrow beams rather than spreading it uniformly in all directions. This creates the illusion of even greater energy output when Earth happens to lie within one of these focused beams. The true energy release may be somewhat lower than calculated, but still represents one of the most efficient energy conversion processes in the known universe. Quantum effects near the magnetar surface may contribute additional energy through processes impossible under normal conditions. The extreme magnetic fields create conditions where the vacuum itself becomes unstable and contributes energy through virtual particle creation and annihilation processes that violate everyday physics. These combined effects make magnetar outbursts the most energetic electromagnetic events in the universe. Cosmic explosions that briefly challenge our understanding of how much energy can be released from objects smaller than terrestrial cities. Einstein revealed that massive objects warp the fabric of space-time like bowling balls placed on a stretched rubber sheet. Our sun creates a gentle depression that keeps planets in their orbits, while black holes create such deep gravitational wells that even light cannot escape. But magnetars twist space-time in ways that challenge our fundamental understanding of reality itself. The magnetar's incredible density creates gravitational effects that go far beyond simple warping. Picture space-time as a flexible fabric that can be stretched, compressed, and twisted in multiple dimensions simultaneously. Near a magnetar's surface, this cosmic fabric becomes so severely distorted that the normal rules of geometry break down completely. At the magnetar surface, space-time curvature becomes so extreme that parallel lines drawn in different directions will actually converge and cross each other, violating basic principles of Euclidean geometry that work everywhere else in our everyday experience. A triangle drawn near the magnetar would have angles that add up to more than 180 degrees. The intense magnetic fields add another layer of space-time distortion that scientists are only beginning to understand. Magnetic forces interact with gravitational effects to create regions where space and time become tangled together like twisted ribbon. This magnetogravitational interaction produces effects that cannot be explained by gravity or magnetism alone. Time dilation near magnetars reaches extreme levels that make science fiction look conservative. Clocks running on the magnetar surface would tick roughly 30% slower than identical clocks in normal space. An hour spent on a magnetar surface corresponds to roughly 85 minutes of time passing for observers far away from the gravitational field. The magnetar's rotation adds rotational frame dragging effects that literally twist space-time around the neutron star, like thick honey stirred by a cosmic spoon. This twisted space-time carries material objects along with the rotation, creating effects similar to being caught in a cosmic whirlpool that extends thousands of miles from the magnetar surface. Light rays traveling near magnetars follow curved paths that can loop completely around the neutron star multiple times before escaping to space. This gravitational lensing effect means that observers could theoretically see multiple images of objects located behind magnetar, each image distorted and magnified by the extreme space-time curvature. The combination of rapid rotation and intense magnetic fields creates gravitational waves with unique characteristics not seen around other astronomical objects. These waves carry information about the magnetar's internal structure and magnetic field configuration encoded in space-time ripples that propagate at light speed throughout the universe. Extreme tidal forces near magnetars stretch space-time itself in different directions. The gravitational field gradient becomes so steep that space-time curvature changes dramatically over distances of just a few miles. This creates regions where the fundamental geometry of space varies significantly from point to point. Quantum effects near the magnetar surface may cause space-time foam, where the smooth fabric of reality becomes bubbly and chaotic at microscopic scales. Virtual particles pop into existence and disappear so rapidly that they affect the local properties of space-time itself, creating fluctuations in the gravitational field. The magnetar essentially becomes a natural laboratory for testing general relativity under conditions far more extreme than anything Einstein could have imagined. These cosmic monsters push the boundaries of space-time physics to absolute limits, where new phenomena emerge. But space-time distortions represent only one aspect of magnetar physics, as their magnetic field lines undergo even more dramatic transformations when pushed beyond their breaking points. Imagine cosmic rubber bands stretched to their absolute breaking point, storing energy equivalent to nuclear explosions while maintaining invisible tension across thousands of miles of space. When magnetar field lines finally snap, they unleash magnetic reconnection events more powerful than anything else occurring in our local universe. The process begins when magnetic field lines become so twisted and stressed that they can no longer maintain their original configuration. Like overstretched cables supporting a bridge, individual field lines start to fray and develop weak points where the magnetic structure becomes unstable. The magnetar's rotation and ongoing magnetic evolution constantly add more stress to these already strained invisible highways. When a field line finally breaks, it does not simply vanish like a snapped rubber band. Instead, the broken ends seek out other magnetic field lines with opposite polarity and connect with them in a process that completely rearranges the magnetic field geometry. This reconnection happens at nearly the speed of light. As magnetic energy converts directly into kinetic energy and electromagnetic radiation, the initial reconnection triggers a cascade effect throughout the magnetosphere. As the newly formed magnetic configuration destabilizes neighboring field lines within microseconds, millions of field lines throughout the magnetar's magnetic environment undergo simultaneous reconnection, releasing stored magnetic energy in a coordinated explosion that can briefly outshine entire galaxies. Charged particles caught in the reconnection zone experience acceleration to incredible speeds as they surf along the rapidly changing magnetic field lines. Electrons and protons reach energies millions of times higher than particles in our most powerful accelerators, creating beams of cosmic rays that stream away from the magnetar at velocities approaching the speed of light. The reconnection process heats surrounding plasma to temperatures exceeding 1 billion degrees, creating conditions hot enough to trigger nuclear fusion reactions in the thin atmosphere above the magnetar surface. This superheated plasma glows intensely in X-ray wavelengths and creates the brilliant flares that astronomers detect from thousands of light years away. Shockwaves generated by magnetic reconnection propagate through the magnetosphere at thousands of miles per second, compressing and heating any material they encounter. These shock fronts can extend millions of miles from the magnetar surface, creating expanding bubbles of superheated plasma that remain detectable for months after the initial reconnection event. The reconnection also generates powerful electromagnetic pulses that sweep across surrounding space like cosmic lightning bolts. These pulses carry enough energy to disrupt radio communications throughout an entire solar system and create aurora displays on any planets within hundreds of light years of the magnetar. Some reconnection events occur deep within the magnetar's magnetosphere, while others happen closer to the neutron star surface, where magnetic field strengths reach their maximum values. Surface reconnection events prove more violent because they involve higher energy density field lines that have been compressed and twisted by the magnetar's extreme gravitational and rotational forces. The reconnection process operates with incredible efficiency, converting nearly 100% of stored magnetic energy into other forms of energy within fractions of a second. This efficiency exceeds any energy conversion process known on Earth and represents one of nature's most effective methods for releasing stored energy. Magnetic reconnection near magnetars provides natural laboratories for studying plasma physics under conditions impossible to recreate in terrestrial experiments. The extreme magnetic field strengths and particle energies involved push reconnection physics into entirely new regimes where quantum effects and relativistic particle behavior become important factors. But magnetic reconnection represents just one aspect of magnetar variability, as some of these cosmic monsters exhibit even stranger behavior patterns that puzzle astronomers worldwide. Most stars shine steadily for billions of years, providing reliable cosmic beacons that astronomers can depend on for consistent observations. Our sun varies its brightness by less than 1% over its 11-year magnetic cycle, creating subtle changes that barely affect Earth's climate. But certain magnetars behave like cosmic light switches, suddenly blazing to life with the intensity of millions of suns before vanishing completely into darkness. These transient magnetars can remain completely invisible to our most sensitive instruments for years or even decades, showing no detectable X-ray emissions despite possessing magnetic fields trillions of times stronger than Earth. Then, without warning, they suddenly activate and become among the brightest X-ray sources in our galaxy, outshining normal stars by factors of millions. The activation process appears to be triggered by internal magnetic instabilities that build up over long periods of dormancy. During quiet phases, the magnetar's magnetic field settles into relatively stable configurations that produce minimal external emissions. But beneath the surface, magnetic stresses continue accumulating as the neutron star's internal magnetic dynamo slowly evolves. When magnetic stress finally exceeds critical thresholds, the magnetar undergoes rapid magnetic field reconfiguration that drastically changes its emission properties. Magnetic field lines that previously remained buried within the neutron star suddenly break through to the surface, creating new channels for particle acceleration and X-ray production. The transition from dormancy to activity can happen in a matter of hours or days, transforming an apparently dead neutron star into one of the most energetic objects in our galaxy. The brightness increase can exceed factors of 1,000, making previously invisible magnetars suddenly visible to X-ray telescopes throughout the solar system. During active phases, these transient magnetars exhibit highly variable emission patterns, with brightness fluctuations occurring on timescales ranging from milliseconds to months. The X-ray output can change by factors of 10 or more within single observing sessions, creating challenging conditions for astronomical observations and theoretical modeling. The active periods typically last anywhere from a few months to several years before the magnetar gradually fades back into dormancy. The fading process appears to be related to the cooling of heated crustal regions and the gradual return magnetic field lines to more stable configurations buried within the neutron star interior. Some magnetars show cyclic behavior with active periods separated by predictable intervals, suggesting that their magnetic field evolution follows quasi-periodic patterns. Others appear completely random in their activation timing, making it impossible to predict when they will next become visible to astronomical observations. The switching behavior may be related to the magnetar's rotation and internal magnetic field geometry. As the neutron star rotates, different magnetic field regions come into view, potentially creating lighthouse-like effects where emissions are beamed in specific directions. Changes in the magnetic field structure can redirect these beams, like causing apparent on-off behavior from Earth's perspective. Crustal fractures and starquakes also influence magnetar visibility by altering the magnetic field configuration near the surface. Major starquakes can suddenly expose previously buried magnetic field lines or bury active field regions, causing dramatic changes in observed emission levels. The transient nature of many magnetars suggests that the total population of these objects in our galaxy may be much larger than current surveys indicate. For every magnetar currently active and detectable, dozens of others may be hiding in dormant states, waiting for the right combination of internal conditions to trigger their next period of violent activity. These cosmic hide-and-seek games reveal that magnetars exist in complex dynamic states that challenge our understanding of neutron star physics and magnetic field evolution in extreme gravitational environments. The atoms that make up everything around us, from the air we breathe to the ground beneath our feet, exist in familiar states where electrons orbit atomic nuclei at comfortable distances determined by electromagnetic forces. But near magnetars, these basic building blocks of matter transform into exotic forms that violate every rule of chemistry and atomic physics we learned in school. A magnetar's magnetic field strength reaches values that completely overwhelm the electromagnetic forces holding electrons in their atomic orbitals. Picture electrons as planets orbiting the sun, but imagine a gravitational field so strong that it rips planets from their orbits and stretches them into needle-thin shapes aligned with the gravitational field lines. At magnetic field strengths exceeding 100 million Tesla, hydrogen atoms become completely unrecognizable. Instead of spherical electron clouds surrounding protons, The atoms stretch into long, thin cigar shapes thousands of times longer than they are wide. The electron orbitals align perfectly with magnetic field lines, creating atomic structures that have no analog anywhere else in the universe. When magnetic field strengths reach 1 billion Tesla, electrons can no longer maintain stable orbits around atomic nuclei. The magnetic force becomes stronger than the electromagnetic attraction between electrons and protons, causing complete atomic ionization. Every atom within thousands of miles of the magnetar surface loses all its electrons, creating a plasma of bare atomic nuclei swimming in a sea of free electrons. The stripped electrons cannot move freely through space because the intense magnetic field constrains their motion to follow magnetic field lines exactly. Picture electrons trapped on invisible highways that spiral around magnetic field lines like cars forced to follow twisting mountain roads. The electrons can only move parallel to magnetic field lines, creating highly directional electrical currents that flow for millions of miles through space. These confined electrons exhibit quantum behavior impossible under normal conditions. In the extreme magnetic environment, electrons can only occupy specific energy levels called Landau levels, which are separated by energy gaps millions of times larger than those found in normal atoms. This creates matter in quantum states that cannot be replicated in any terrestrial laboratory. The magnetic field also affects the fundamental properties of empty space itself. At field strengths approaching magnetar levels, the quantum vacuum becomes birefringent, meaning that light waves polarized in different directions travel at slightly different speeds. This effect, called vacuum birefringence, transforms empty space into a medium with optical properties similar to certain crystals. Photons traveling through the magnetized vacuum near magnetars can undergo splitting or merging processes that are forbidden under normal electromagnetic theory. High-energy gamma rays can split into multiple lower-energy photons, while multiple X-rays can combine into single gamma rays through magnetic field interactions with virtual particles in the quantum vacuum. The magnetar environment creates conditions where the Pauli exclusion principle, which normally prevents electrons from occupying the same quantum state, becomes modified by magnetic effects. Electrons can be compressed into configurations with much higher densities than normally possible, creating degenerate electron matter that exhibits properties intermediate between normal atoms and neutron star nuclear matter. Matter falling onto magnetar surfaces undergoes complete atomic disintegration, long before reaching the neutron star itself. The intense radiation pressure and magnetic forces strip away electrons, break apart molecular bonds, and even disrupt atomic nuclei. In some cases, only individual protons, neutrons, and electrons survive the journey to the magnetar surface. These extreme matter states provide natural laboratories for testing quantum mechanics and atomic physics under conditions that push theoretical models to their absolute limits, revealing new phenomena that expand our understanding of how matter behaves in the universe's most extreme environments. But magnetars do more than just destroy familiar forms of matter. They also play crucial roles in creating the heavy elements that make planets and life possible. Every atom in your body, except hydrogen, was forged inside stars and scattered through space by cosmic explosions. The calcium in your bones, the iron in your blood, and the oxygen you breathe all originated from nuclear furnaces burning billions of years ago. But some of the heaviest and rarest elements essential for life may owe their existence to magnetars and their incredible magnetic violence. Traditional stellar nucleosynthesis, the process by which stars create heavy elements through nuclear fusion, can produce elements up to iron in the periodic table. Elements heavier than iron require different conditions because fusing them together consumes energy rather than releasing it. Creating gold, platinum, uranium, and other heavy elements demands environments with extreme neutron densities and temperatures that exceed anything found in normal stellar cores. Magnetar explosions provide exactly these extreme conditions during their most violent outbursts. When magnetic field lines carrying enormous stored energy suddenly reconnect, they heat surrounding material to temperatures exceeding 1 billion degrees, while simultaneously compressing matter to densities approaching those found in atomic nuclei. These conditions allow rapid neutron capture processes that build heavy elements in seconds. The rapid neutron capture process, called the R process, occurs when atomic nuclei absorb neutrons faster than they can undergo radioactive decay. This creates neutron-rich isotopes that would normally be unstable but can capture additional neutrons before decaying. The process builds up heavy elements by adding neutron after neutron to lighter seed nuclei. Magnetars provide ideal R process conditions because their violent magnetic reconnection events create neutron fluxes trillions of times higher than those found in normal stellar environments. The combination of extreme temperature, density, and neutron abundance allows magnetar explosions to synthesize elements all the way up to uranium and beyond in the periodic table. The magnetic field geometry around magnetars influences how newly created heavy elements get distributed through space. Charged particles carrying fresh heavy elements follow magnetic field lines that extend millions of miles from the neutron star surface, creating directional jets that spray heavy elements across vast regions of interstellar space. These magnetar-generated heavy element jets can travel at speeds approaching the speed of light, carrying their precious cargo thousands of light years from the original explosion site. When these jets interact with surrounding interstellar gas clouds, they deposit heavy elements that eventually get incorporated into new generations of stars and planets. Some of the rarest heavy elements found on Earth may have magnetar signatures in their isotopic ratios. Different nucleosynthesis processes create heavy elements with slightly different mixtures of isotopes, like cosmic fingerprints, that reveal their origins. Elements created in magnetar explosions should exhibit specific isotopic patterns that distinguish them from heavy elements produced by other astrophysical processes. Magnetars may be particularly important for creating elements heavier than gold, including platinum, iridium, and the heaviest naturally occurring elements. These ultra-heavy elements require the most extreme neutron flux conditions, which may only occur during the most violent magnetar hyperflares and magnetic reconnection events. The heavy elements created by magnetars eventually become incorporated into dust grains that drift through interstellar space for millions of years. These enriched dust particles serve as condensation nuclei around which planets form, ensuring that magnetar-created elements become part of solid worlds where life can potentially develop. Recent astronomical observations suggest that galaxies with higher rates of magnetar activity also tend to have higher abundances of heavy elements in their interstellar medium. This correlation supports the idea that magnetars serve as important heavy element factories that help enrich the chemical complexity of the universe over cosmic time. The violent magnetic processes that make magnetars so dangerous to nearby life may paradoxically be essential for creating the chemical diversity that makes complex chemistry and biology possible throughout the universe. For the past 15 years, astronomers have detected brief but incredibly intense bursts of radio waves coming from random directions across the sky. These fast radio bursts last only milliseconds, but release more energy in radio frequencies than our sun produces at all wavelengths in an entire day. The sources remain invisible to optical telescopes, creating one of modern astronomy's most perplexing mysteries. Each fast radio burst appears as a brilliant flash of radio energy that sweeps across different frequencies in a characteristic pattern. Lower frequency radio waves arrive slightly later than higher frequencies, suggesting that the signals have traveled through ionized material that disperses radio waves like a prism splits white light into colors. The dispersion measurements indicate that most fast radio bursts originate from distances of billions of light years, making them among the most energetic radio events in the observable universe. The energy requirements seemed impossible to explain until astronomers began connecting these mysterious signals to magnetar activity in our own galaxy. In April 2020, radio telescopes detected a fast radio burst coming from within the Milky Way for the first time. The signal originated from SGR 1935 plus 2154, a known magnetar located about 30,000 light-years from Earth. This discovery provided the first direct evidence linking fast radio bursts to magnetar activity. The magnetar-generated fast radio burst coincided with X-ray and gamma-ray emissions detected by space telescopes, confirming that the radio signal was produced during a violent magnetic reconnection event. The simultaneous multi-wavelength observations revealed that magnetar outbursts can produce intense radio emissions along with their characteristic X-ray flares. The radio emission mechanism likely involves coherent radiation from relativistic electrons accelerated along magnetic field lines during magnetic reconnection events. When billions of electrons move together in synchronized motion, they can produce radio waves with intensities far exceeding what individual electrons could generate through normal synchrotron radiation processes. Magnetar radio bursts exhibit several characteristics that match observations of extragalactic fast radio bursts, including their millisecond durations, frequency dispersion patterns, and enormous energy outputs. The main difference lies in the distances involved. Extragalactic events appear much brighter because they originate from magnetars in distant galaxies with different surrounding environments. Some fast radio bursts repeat at irregular intervals, producing multiple flashes from the same source over periods of months or years. This repetitive behavior matches the intermittent activity patterns observed from known magnetars, which can remain dormant for long periods before undergoing series of violent outbursts. The rate of fast radio burst detections, roughly 1,000 per day across the entire sky, matches theoretical predictions for the expected rate of magnetar flares in galaxies throughout the observable universe. If every galaxy contains populations of active magnetars similar to our Milky Way, the combined flare activity would produce fast radio bursts at approximately the observed rate. Advanced radio telescope arrays now routinely search for fast radio bursts while simultaneously monitoring known magnetars for X-ray activity. These coordinated observations aim to catch more magnetar radio bursts in the act and determine what fraction of magnetar outbursts produce detectable radio emissions. The magnetar connection suggests that fast radio bursts serve as cosmic beacons announcing the presence of highly magnetized neutron stars in distant galaxies where individual magnetars are too faint to detect directly. Each burst provides a brief glimpse into extreme magnetic field physics, operating billions of light years away. Understanding the magnetar fast radio burst connection could revolutionize our knowledge of neutron star populations throughout the universe and provide new tools for studying magnetic field evolution in environments far more extreme than anything accessible through direct observation. But the cosmic threat posed by these invisible magnetic monsters extends far beyond mysterious radio signals, raising questions about what would happen if one appeared too close to Earth. The nearest known magnetar lies approximately 9,000 light-years from Earth, safely distant in the constellation Cassiopeia. At this range, even the most violent magnetar outbursts pose no direct threat to life on our planet. But astronomers have calculated exactly how close these magnetic monsters would need to approach before their deadly influence could trigger mass extinction events that would rival the asteroid impact that killed the dinosaurs. A magnetar located within 1,000 light-years of Earth would pose the first serious threat to our planet's biosphere through its intense X-ray and gamma-ray emissions. During major outbursts, the high-energy radiation would strip away significant portions of Earth's protective ozone layer, allowing deadly ultraviolet radiation from our sun to reach the planet's surface at lethal intensities. The ozone depletion would occur gradually over several months following a magnetar hyperflare, creating a delayed extinction mechanism that would be difficult to predict or prepare for. Marine ecosystems would collapse first as phytoplankton die from increased UV exposure, followed by terrestrial plant life and eventually entire food chains that depend on photosynthetic organisms. At distances of 500 light-years, magnetar outbursts would deliver radiation doses equivalent to nuclear weapons detonating continuously in Earth's upper atmosphere for several minutes. The gamma rays would create nitrogen oxides that would not only destroy ozone, but also create a brown atmospheric haze that would significantly reduce sunlight reaching Earth's surface. The combination of increased UV radiation and decreased visible light would create impossible conditions for most complex life forms. Plants would simultaneously suffer from radiation damage and insufficient photosynthesis, while animals would face both direct radiation poisoning and ecosystem collapse as their food sources disappeared. A magnetar within 100 light-years would pose an immediate extinction threat even during relatively minor outbursts. The X-ray flux would be intense enough to heat Earth's upper atmosphere and cause significant atmospheric loss to space. Our planet would begin losing its protective atmospheric envelope, following a path similar to Mars during its early history. At 50 light-years distance, major magnetar flares would deliver radiation equivalent to detonating nuclear weapons across Earth's entire surface simultaneously. The energy input would trigger massive climate disruption, potentially ending the current ice age and causing global temperature increases of tens of degrees within decades. The magnetic field effects become important at distances closer than 20 light-years, where even minor magnetar activity would disrupt Earth's magnetic field and allow deadly solar wind particles to reach our planet's surface. The aurora displays would extend to tropical regions as charged particles from both the sun and magnetar interact chaotically with our compromised magnetic environment. Within 10 light-years, a magnetar would dominate our local magnetic environment completely. Earth's magnetic field would be overwhelmed and possibly reversed, causing our protective magnetosphere to collapse entirely. The planet would become directly exposed to cosmic ray bombardment that would make the surface uninhabitable for any life form larger than bacteria. At distances closer than 5 light-years, the magnetar's intense magnetic field would begin affecting the structure of Earth's atmosphere directly. The magnetic forces would ionize atmospheric gases and create powerful electrical currents that would generate continuous lightning storms and aurora activity across the entire planet. A magnetar within 1 light-year would represent an absolute extinction event that would sterilize Earth's surface within hours of any significant outburst. The magnetic field strength would be sufficient to disrupt chemical bonds in biological molecules, making life impossible even in the deepest ocean trenches or most protected underground environments. Fortunately, stellar dynamics make close magnetar encounters extremely unlikely. These objects form from massive stars that typically exist in different galactic regions than our Sun, and their motion through space follows predictable gravitational patterns that keep them far from our solar system. However, the extreme distances at which magnetars can threaten life reveal just how powerful these cosmic monsters truly are when they unleash their full magnetic fury on an unsuspecting universe. Throughout the universe, gravity slowly pulls objects together in cosmic dances that span millions of years. Binary star systems gradually spiral inward as they lose energy to gravitational waves, eventually leading to catastrophic collisions that can be detected from billions of light-years away. But when two magnetars approach each other for the ultimate cosmic collision, they create conditions so extreme that physics itself approaches its breaking point. The collision process begins millions of years before the actual impact, as two magnetars in a binary system slowly spiral toward each other. Gravitational waves carry away orbital energy at an accelerating rate, causing the neutron stars to orbit faster and move closer together with each passing century. As the magnetars approach within a few thousand miles of each other, their individual magnetospheres begin to interact in chaotic, unpredictable ways. Magnetic field lines from each neutron star connect and reconnect explosively, creating bursts of energy that would vaporize entire planets instantly. These preliminary magnetic interactions serve as cosmic warning shots for the ultimate catastrophe to come. The final moments before collision happen faster than human comprehension can follow. In the last second, the two magnetars complete dozens of orbits while accelerating to speeds approaching 20% the speed of light. Their combined gravitational field becomes so intense that space-time itself begins to ripple violently, sending gravitational waves throughout the universe at light speed. The collision itself defies description in familiar terms. Two objects, each containing more mass than our Sun, compressed into volumes smaller than Manhattan, smashed together with kinetic energies exceeding the total gravitational binding energy of entire solar systems. The impact creates temperatures that rival conditions inside the Big Bang itself during the first microseconds after the universe began. The merged magnetic fields create the strongest magnetic environment possible in the current universe, with field strengths that approach theoretical limits imposed by quantum mechanics. These ultra-strong fields warp space-time so severely that the normal distinction between space and time becomes meaningless near the collision site. Matter caught between the colliding magnetars undergoes complete nuclear disintegration as magnetic forces overcome the strong nuclear force that normally holds atomic nuclei together. Protons and neutrons break apart into their constituent quarks and gluons, creating a quark-gluon plasma that last existed during the first microseconds after the Big Bang. The collision ejects streams of ultra-dense matter at velocities approaching the speed of light. These matter jets carry magnetic fields trillions of times stronger than anything found elsewhere in the modern universe, creating cosmic particle accelerators that boost individual atoms to energies exceeding those in our most powerful terrestrial machines by factors of billions. The gravitational waves produced during magnetar merger events carry distinctive signatures that reveal information about the extreme physics operating during the collision. Future gravitational wave detectors may be sensitive enough to detect the unique waveforms produced when ultra-strong magnetic fields interact with curved spacetime during the final moments before impact. The explosion creates gamma-ray bursts with energies that exceed normal magnetar hyperflares by factors of thousands. These merger-driven bursts can briefly outshine entire galaxy clusters and remain detectable across billions of light-years of cosmic distance, making them among the most energetic electromagnetic events in the observable universe. The collision aftermath may create short-lived objects with magnetic fields approaching the absolute theoretical maximum allowed by physics, where magnetic energy density equals the rest mass energy density of matter itself. These ultramagnetars would exist for only milliseconds before collapsing into black holes or disintegrating explosively. The heavy elements synthesized during magnetar collisions include isotopes that cannot be created through any other known astrophysical process, potentially explaining the origins of some rare elements found in meteorites and terrestrial ore deposits. But magnetars do not distribute themselves randomly throughout our galaxy, instead showing mysterious clustering patterns that reveal secrets about their formation and evolution. When astronomers plot the locations of known magnetars on maps of our Milky Way galaxy, a striking pattern emerges. These magnetic monsters are not scattered randomly throughout the galactic disk, like many other types of stars. Instead, they cluster heavily in specific regions while remaining completely absent from vast areas of space, creating a cosmic geography that reveals fundamental truths about magnetar formation and galactic evolution. The highest concentration of magnetars lies within the inner 10,000 light-years of our galaxy, particularly near the galactic center, where stars are packed together at densities thousands of times higher than in our local neighborhood. This central region contains nearly half of all known magnetars, despite representing only a tiny fraction of the galaxy's total volume. The clustering pattern reflects the distribution of massive stars that serve as magnetar progenitors. Massive stars capable of becoming magnetars form preferentially in regions with high gas densities and active star formation. These conditions exist primarily near the galactic center and in the spiral arms where gravitational compression triggers rapid stellar birth. Young star-forming regions along the spiral arms contain second highest magnetar concentrations, particularly in areas where recent supernovae have compressed surrounding gas clouds and triggered waves of new stellar formation. The Cygnus region, located about 6,000 light-years from Earth, hosts several magnetars born from a burst of massive star formation that occurred roughly 10 million years ago. The galactic halo, a spherical region surrounding the main disk of our galaxy, contains virtually no known magnetars. This absence reflects the halo's low metallicity and lack of recent star formation activity. The ancient stars in the galactic halo formed before heavy elements became abundant enough to support the formation of massive stars with strong magnetic fields. Magnetar clustering also correlates with supernova remnants and other signs of recent massive star death. Many magnetars lie within or near expanding shock waves created by stellar explosions, suggesting that magnetar formation often occurs in regions where multiple massive stars live and die in close proximity over relatively short cosmic timescales. The local bubble, a cavity in the interstellar medium surrounding our solar system, contains no known magnetars within several hundred light-years of Earth. This void likely resulted from ancient supernovae that cleared away the gas needed for massive star formation, while simultaneously driving away any existing massive stars through gravitational interactions. Globular clusters, dense stellar associations containing hundreds of thousands of old stars, were once thought to be likely magnetar hiding places due to their high stellar densities. However, observations reveal that globular clusters contain few or no magnetars, probably because their ancient stellar populations formed before conditions suitable for magnetar creation became common. The gap between spiral arms shows significantly reduced magnetar density compared to the arms themselves. This pattern reflects the temporary nature of spiral arm structure, where gas compression triggers bursts of star formation that move through the galaxy like slow-motion waves, leaving behind clusters of massive stars and their eventual neutron star remnants. Some magnetars appear to be runaway objects traveling at high speeds through regions where they could not have formed originally. These high-velocity magnetars may have received gravitational kicks during their formation process or through interactions with other massive objects, launching them on trajectories that carry them far from their birthplaces. The distribution pattern suggests that magnetar formation requires specific environmental conditions that are not uniformly available throughout our galaxy. High metallicity, dense gas clouds, and active star formation all contribute to creating the massive, highly magnetized progenitor stars needed for magnetar birth. Future surveys with more sensitive X-ray telescopes will likely reveal additional magnetars in previously unexplored regions of our galaxy, potentially uncovering new clustering patterns that provide insights into the complex relationship between galactic environment and magnetar formation physics. Understanding magnetar distribution patterns helps astronomers predict where to search for new examples of these elusive objects and provides clues about how galaxies evolve chemically and magnetically over cosmic time. Einstein's theories of special and general relativity have withstood every experimental test for over a century, accurately predicting everything from GPS, satellite corrections to gravitational wave detections. These theories describe space, time, gravity, and motion with mathematical precision that works flawlessly under almost all conditions found in our universe. But magnetars operate in such extreme environments that they push Einstein's physics into uncharted territory where new phenomena emerge. General relativity describes gravity as the curvature of space-time caused by mass and energy, predicting that massive objects create gravitational wells that affect the motion of matter and light. Near magnetars, this curvature becomes so severe that spacetime approaches the mathematical singularities that mark the breakdown of Einstein's equations. Similar to dividing by zero in ordinary arithmetic, the combination of extreme gravity and ultra-strong magnetic fields creates conditions not considered in Einstein's original formulations. While general relativity handles pure gravitational effects with perfect accuracy, it does not fully account for how magnetic fields interact with curved spacetime when both reach magnetar-level intensities. Magnetars generate gravitational time dilation effects so strong that time passes significantly surfaces compared to distant regions of space. But their magnetic fields also create additional relativistic effects through electromagnetic field energy that contributes to the overall spacetime curvature, creating corrections to Einstein's predictions that become measurable under magnetar conditions. The magnetic field strength near magnetars approaches the critical field strength where quantum mechanics begins to modify the behavior of empty space itself. At these intensities, the quantum vacuum becomes birefringent and starts to scatter light through processes that classical general relativity does not predict, requiring corrections from quantum film field theory. Particle motion near magnetars follows trajectories that combine gravitational acceleration with magnetic forces operating at relativistic intensities. The resulting particle paths cannot be calculated using either general relativity or classical electromagnetism alone, requiring new mathematical frameworks that merge both theories under extreme conditions. The rapid rotation of magnetars creates frame-dragging effects that literally twist space-time around the neutron star like thick honey stirred with a cosmic spoon. Combined with magnetic field rotation, this creates magnetorotational instabilities that generate gravitational wave patterns not predicted by standard general relativity applied to non-magnetic rotating bodies. Magnetars may produce gravitational waves through magnetic field oscillations rather than just through mass motions, creating gravitational radiation with characteristics that extend beyond Einstein's original predictions. These magnetogravitational waves could carry information about magnetic field structure encoded in space-time ripples that propagate throughout the universe. The extreme magnetic fields near magnetars cause virtual particles in the quantum vacuum to behave as if empty space has acquired optical properties similar to physical materials. Photons traveling through this magnetized vacuum experience refraction, dispersion, and scattering effects that require modifications to general relativity's treatment of electromagnetic wave propagation. Some theoretical models suggest that magnetars with the strongest magnetic fields may violate the cosmic censorship conjecture, a key assumption in general relativity that prevents naked singularities from forming outside black hole event horizons. If confirmed, this would represent a fundamental limitation of Einstein's theory. Under the most extreme magnetic conditions, the energy density stored in magnetar magnetic fields approaches levels where it contributes measurably to the gravitational field strength, creating situations where electromagnetic field energy acts as a significant source of space-time curvature. This electromagnetic contribution to gravity requires extensions to Einstein's field equations that include magnetic field stress energy terms. Magnetars also provide natural laboratories for testing whether the fundamental constants of nature, such as the fine structure constant that determines electromagnetic interaction strength, remain truly constant under extreme conditions. Any variation in these constants would show up as deviations from Einstein's predictions in magnetar observations. The study of magnetar physics pushes theoretical physicists to develop new mathematical frameworks that unify general relativity with quantum mechanics and electromagnetism, potentially leading to breakthrough discoveries that extend our understanding of space, time, and matter beyond Einstein's revolutionary but incomplete vision. But to study these cosmic monsters and test the limits of physics requires cutting-edge technology that pushes human engineering capabilities to their own extreme limits. Magnetars emit virtually no visible light, making them completely invisible to the optical telescopes that revealed most astronomical discoveries throughout history. These magnetic monsters hide in the darkness of space, revealing their presence only through intense X-ray and gamma-ray emissions that require sophisticated space-based observatories to detect and study from Earth's protective distance. The Chandra X-ray Observatory, launched in 1999, revolutionized magnetar astronomy with its unprecedented ability to detect faint X-ray sources and measure their positions with incredible precision. Chandra's mirrors focus X-rays using grazing incidence reflection, similar to skipping stones off water, because X-rays would penetrate normal telescope mirrors designed for visible light. The Nuclear Spectroscopic Telescope Array, known as NuSTAR, specializes in detecting high-energy X-rays that carry information about the most energetic processes occurring near magnetar surfaces. Its focusing optics concentrate X-rays onto sensitive detectors that can measure individual photon energies and arrival times with microsecond precision. Swift's gamma-ray burst mission serves as an automated magnetar hunter, scanning the entire sky continuously for sudden bursts of gamma rays that might indicate magnetar activity. When Swift detects a burst, it automatically redirects its telescopes toward the source and transmits alerts to observatories worldwide within minutes of the initial detection. The Fermi Gamma Ray Space Telescope monitors the entire sky every 3 hours, creating detailed maps of gamma-ray sources throughout our galaxy. Fermi's Large Area Telescope can detect the extended gamma-ray emissions that surround active magnetars and track changes in their emission patterns over years of continuous observation. Ground-based radio telescope arrays like the Very Large Array in New Mexico search for radio emissions from magnetars during their active phases. These radio signals provide complementary information about magnetar magnetospheres, that cannot be obtained from X-ray observations alone, revealing details about plasma conditions thousands of miles from neutron star surfaces. The Event Horizon Telescope, famous for imaging black holes, also studies magnetar environments using very long baseline interferometry techniques that combine signals from radio dishes separated by thousands of miles. This creates virtual telescopes larger than Earth itself, capable of resolving magnetic field structures near magnetar surfaces. Advanced computer simulations running on supercomputers model magnetar magnetic field evolution using magnetohydrodynamics equations that describe how magnetic fields interact with plasma under extreme conditions. These simulations require months of computing time on the world's most powerful supercomputers to model just seconds of real magnetar activity. Machine learning algorithms analyze vast databases of X-ray observations to identify subtle patterns in magnetar emissions that human astronomers might miss. Neural networks trained on known magnetar data can automatically classify new X-ray sources and predict which ones are likely to be previously undiscovered magnetars. Gravitational wave detectors like LIGO and Virgo now search for the space-time ripples that magnetars produce during starquakes and magnetic reconnection events. These detectors use laser interferometry to measure changes in space-time smaller than 1/10,000th the width of a proton, potentially revealing gravitational signals from magnetar activity. Next-generation X-ray observatories currently under development will surpass current capabilities by factors of hundreds. The European Space Agency's Athena mission will combine large collecting areas with high spectral resolution, enabling detailed studies of magnetar atmospheres and magnetic field structures. Artificial intelligence systems now analyze multi-wavelength observations from dozens of different telescopes simultaneously, searching for correlations between magnetar activity at different energy ranges. These AI systems can process observation data faster than human researchers and identify complex patterns that span multiple wavelengths and timescales. Quantum sensors under development for future space missions may be sensitive enough to detect the gravitational wave signatures of magnetar starquakes from across our galaxy, opening entirely new windows for studying these magnetic monsters through their effects on space-time itself. The combination of space-based observatories, ground-based telescopes, supercomputer simulations, and artificial intelligence creates a comprehensive toolkit for studying objects so extreme they challenge our understanding of physics itself. These technological marvels may soon reveal that magnetars hold keys to solving some of the universe's deepest mysteries, including the nature of dark matter that comprises most of our cosmos. Astronomers have discovered that ordinary matter, the atoms and molecules that make up stars, planets, and everything we can see, comprises only 5% of the universe's total mass and energy. The remaining 95% consists of dark matter and dark energy, mysterious components that interact with ordinary matter only through gravitational effects. But magnetars may provide crucial clues to solving this cosmic puzzle. Dark matter reveals its presence through gravitational effects on visible matter, bending light from distant galaxies and affecting the rotation speeds of spiral galaxies like our Milky Way. Yet, dark matter particles have never been directly detected. Despite decades of increasingly sophisticated experiments designed to catch them interacting with ordinary atoms in underground laboratories, magnetars create the most extreme magnetic field environments in the known universe. Conditions where exotic physics, processes that normally remain hidden, might become detectable. If dark matter particles possess any magnetic properties or can be converted into ordinary matter under extreme conditions, magnetars would be the most likely places for such interactions to occur. Some theoretical models propose that dark matter consists of axions, hypothetical particles that would interact very weakly with magnetic fields under normal conditions. But in the ultra-strong magnetic fields surrounding magnetars, axions might convert into detectable photons through a process called the Primakov effect, creating characteristic X-ray emissions that could distinguish magnetars harboring axion dark matter. The magnetic field strengths near magnetars approach levels where quantum vacuum effects become important, potentially creating conditions where dark matter particles could be produced from pure, electromagnetic energy. These magnetar-generated dark matter particles might have different properties than primordial dark matter created during the Big Bang, providing new insights into dark sector physics. Magnetar timing observations, which measure the precise arrival times of X-ray pulses with microsecond accuracy, might reveal gravitational effects from dark matter concentrations too small to detect through other astronomical methods. If dark matter clumps passing near magnetars could create tiny timing variations that would be invisible in observations of ordinary pulsars, but detectable in the more energetic emissions from magnetars. Some models suggest that dark matter could accumulate preferentially around magnetars due to their extreme gravitational fields and magnetic interactions. This dark matter concentration might affect magnetar spin-down rates, magnetic field evolution, or emission patterns in ways that would provide indirect evidence for dark matter particle properties. The violent magnetic reconnection events in magnetar magnetospheres create particle energies that rival those in our most powerful accelerators, potentially producing dark matter particles through high-energy collision processes. If dark matter can be created from ordinary matter under extreme conditions, magnetar outbursts would be natural dark matter factories operating throughout the universe. Magnetars might also help explain the apparent shortage of antimatter in our universe through magnetic field effects on matter-antimatter interactions. The extreme magnetic fields could influence the behavior of any primordial antimatter or create conditions that preferentially produce matter over antimatter during violent reconnection events. The gravitational waves produced by magnetar star quakes carry information about the internal structure and composition of neutron stars, potentially revealing whether dark matter particles can exist stably inside ultra-dense stellar cores. Any dark matter component within magnetars would affect their gravitational wave signatures in detectable ways. Future X-ray observatories with improved sensitivity might detect the faint signatures of axion-photon conversion around magnetars, providing the first direct evidence for axion dark matter and solving one of cosmology's greatest mysteries. The characteristic energy spectra and polarization patterns of these converted photons would serve as smoking gun evidence for dark matter detection. Magnetars in different galactic environments, from the dense central regions to the sparse outer halo, experience different dark matter densities that might affect their observable properties. Systematic studies of magnetar populations throughout our galaxy could reveal dark matter distribution patterns invisible through other astronomical techniques. The extreme physics operating in magnetar environments might also reveal connections between dark matter and dark energy, the mysterious force driving cosmic acceleration. If these dark components are related through physics beyond our current theories, magnetars provide natural laboratories where such connections might become apparent. Understanding how magnetars interact with dark matter could revolutionize both neutron star physics and cosmology, potentially solving the dark matter mystery while revealing new aspects of physics in the universe's most extreme magnetic environments. But even magnetars cannot last forever, and their ultimate fate reveals the distant future that awaits all matter in our expanding universe. The universe we see today, filled with shining stars and active galaxies, represents just the opening chapter in cosmic history. Our universe is only 14 billion years old, practically an infant compared to the trillions of years of cosmic evolution that lie ahead. As the universe expands and cools, magnetars will be among the last objects to succumb to the heat death that awaits all matter and energy. In the first trillion years of cosmic future, magnetars will gradually lose their intense magnetic fields through a process called magnetic field decay. The electrical currents flowing through neutron star crusts that maintain these incredible magnetic fields will slowly dissipate as the ultra-dense matter undergoes gradual changes in its crystalline structure and superconducting properties. As magnetic fields weaken, magnetars will transform into ordinary neutron stars that emit only faint thermal radiation from their slowly cooling surfaces. The violent X-ray outbursts and gamma-ray flares that make young magnetars so spectacular will fade away, leaving behind invisible objects detectable only through their gravitational effects on nearby matter. The cooling process for neutron stars spans hundreds of billions of years. As these ultra-dense objects slowly radiate away their internal thermal energy, even after their magnetic fields decay completely, former magnetars will remain among the hottest objects in the universe for cosmic ages, glowing dimly in infrared wavelengths long after all normal stars have burned out. By the time the universe reaches 100 trillion years of age, star formation will cease completely as galaxies exhaust their supplies of hydrogen and helium fuel. The last red dwarf stars will continue burning for trillions of additional years, but eventually, even these long-lived stellar embers will fade to darkness, leaving magnetars as among the few remaining sources of energy in an increasingly cold cosmos. During this stelliferous era's twilight, some magnetars may capture dark matter particles from their surroundings and convert their mass into energy through unknown dark sector interactions. This process could provide magnetars with new energy sources that extend their active lifetimes far beyond what normal thermodynamics would predict, potentially making them the last active objects in the visible universe. In the deep cosmic future, after 10 to the 34th years have passed, proton decay may begin breaking down the atomic nuclei that comprise magnetar cores. If theoretical predictions prove correct, even the ultra-stable nuclear matter inside neutron stars will gradually dissolve as individual protons spontaneously decay into lighter particles and energy. The proton decay process would cause magnetars to slowly evaporate from the inside out, converting their enormous mass into elementary particles and radiation over timescales that dwarf the current age of the universe by factors of trillions of trillions. The final magnetars would shine briefly as they undergo this ultimate decay process. Some magnetars might avoid proton decay by collapsing into black holes during their cooling phase, particularly those with masses close to the theoretical maximum for neutron star stability. These magnetar origin black holes would persist much longer than their neutron star counterparts, slowly evaporating through Hawking radiation over periods of 10 to the 67th years. If the universe undergoes accelerating expansion driven by dark energy, magnetars will eventually become isolated islands of matter in an increasingly empty cosmos. The space between galaxies will stretch so much that individual magnetars will lose all contact with other matter, floating alone through infinite darkness. In some cosmological scenarios, the universe might undergo a big rip, where accelerating expansion becomes so extreme that it overcomes all fundamental forces, tearing apart galaxies, stars, and eventually atomic nuclei themselves. Under these conditions, magnetars would be among the last objects to survive before space-time expansion overcomes even the nuclear forces holding neutron star matter together. Alternative cosmic futures might see magnetars play roles in triggering universe-scale phase transitions or serving as seeds for new forms of matter that emerge under conditions impossible during the current cosmic epoch. The extreme physics operating inside magnetars might provide transition pathways to entirely new states of matter and energy. The ultimate fate of magnetars remains intimately connected to unsolved questions about dark energy, proton stability, and the fundamental nature of space-time itself, making these magnetic monsters potential witnesses to cosmic events that will unfold over time periods beyond human imagination. In the end, magnetars represent both the universe's most extreme present-day phenomena and possible keys to understanding the ultimate destiny that awaits all matter and energy in our expanding cosmos.